Hey everybody, my name is Alex Laggy, and I'm going to be giving a presentation today about the data science project that I've been working on with David and Matt, Jamie and Justin here these past 3-4 months now, and just kind of show the new technology that we have and the new capability that we're trying to bring into Keyhole with regards to the data science department. So just a quick overview and an introduction about myself. Again, my name's Alex. I'm graduating with a data science degree here actually tomorrow. So I went for my master's in data science. I had a computer engineering background. So this is kind of a merger of all of my skills into this data science project. So we're also going to go over just the data mining process in general, how it works, and this is going to be more of a technical portion of it, the technologies we used in our process in general, and then just some future goals with the data science department in general, as well as our project in general. And then we'll also go, I'll let you guys ask questions at the end if you didn't have a chance to speak up at all during it. So first, the most important thing of data science in general is understanding what the problem is. So for our project, what we were working on is we wanted to calculate how fast a river in Norfork, Arkansas was flowing at a certain U.S. Geological Survey point. So the reason why we want to know about this is I think, first of all, there's some avid fishermen in the company. So there are farmers downrange that are rice farmers that need to experience the flooding, handle when the river is going to be flooding faster or more water is going to be come through, so they can make accurate preparations for whenever the river is going to be flowing higher. So let's go to what the results were of this project in general. This is just kind of quick and easy over what happened, and then I'll go into more technical details. So first off, what we have is we have a prediction for how fast the river is going to be flowing for up to 4 days out. So, and then we also had a final model score, an R squared of 0.847. And what you can basically think of this as is it's the accuracy of the model in more layman's terms. And then we also allow the users to text the Convo app to see the predictions. So I'll show you guys a slide on that later, but it's all built into the current Heroku app that we have in Keyhole for the river in general in that area. So let's talk about just the process in general and what we needed to do to come to our results. So I really like to follow the data mining process. First, the most important part, well, probably the first or second most important part in the data mining process is going to be your business understanding and understanding what the problem is. There's always going to be things that you might not know about what is going on in the process in general, and I'll go into more details about where we've used this cycle effectively through our stakeholder meetings to go back and forth between data understanding, business understanding, preparation, and all of that in the peer cycle. But in the business understanding side, you really want to know what are we even trying to predict and what is actually affecting it, and what are the input variables that are changing our target whatsoever. Next, we go into the data understanding, where we just need to figure out now that we know what we're looking for and what we want to predict, what do we know about the data that we have? What data do we need to get? Where can we get these data sources, and how reliable is the data that we have? A pretty big tenet of data science in general is you can put any data you want into a model and it will predict something. But if you put in garbage, you're going to get garbage back out. So it's important to know that the data that you're using is actually related to your problem. Next, there's the data preparation. This is called data cleaning, data massaging. There's a multitude of words for it in data science in general. But this is where you're going to transform your data set from raw data combine them all together to your final data frame that you're using for your actual model. Then you'll handle some other pieces of the data preparation or other pieces that I'll go into more detail about when we get to that slide. The modeling, that's the fun part of data science. That's where what people actually think of data science as a whole is the data modeling part. That's where you get to use all the fun algorithms, fancy models to actually make your predictions. Then you need to do evaluation where you look, see what results do we get back? Do they make sense with our business understanding? How do we need to tune our models better to actually make sure that we are getting the proper results that we're expecting, or maybe we find some new results that we weren't. And then finally, we will deploy it. And because no model is worth anything, nobody can ever use it or reach it. And the predictions are never able to be seen. So let's go more in depth to what is actually going on in our problem. So as you can see from my map I expertly drew up, we have the Bull Shoals Dam and the Norfolk Dam. And then there's also that gauge right around here in Norfolk, where we're actually collecting our CFS results, or cubic feet per second of the river. So you can see that the Bull Shoals Dam will feed in a pretty long path to get all the way to this gauge, where Norfolk Dam is much closer and goes there a lot quicker. So whenever we first started this, whenever I first looked at the problem, I understood, we've got this gauge, we have the Norfolk Dam right here that is feeding in there. But what we didn't know, or I didn't know at the time, was that there was also this dam all the way up here that was also causing flow rates into the gauge. And by using our weekly stakeholder meetings, I was able to get more of an understanding from David about what was actually all happening here. And I think that that's probably one of the most important things in consulting in general, and especially for data science, is that you get all of the pieces together of all the possible variables that can affect your target. I had no idea that, this dam flooded in at all. But by understanding more about how it worked from David, we were able to get that added into the model and help increase our results by a lot. And as you can see, we've got some happy fly fishermen and rice farmers that will be able to use what we predict to get a better understanding of what is going to be happening in the future. So now let's go to the data understanding / gathering all the data. So first off, we had to use a variety of different sources in order to get all the data we needed. First, I used web scrapers in Python using a Celerium, which is just a web scraping package that's in Python, to scrape the U.S. Geological Survey and the Army Corps of Engineers for data. So the USGS data source is where we're getting all of our CFS data and the location that and the location of the gauge, actually, because there's lots of other gauges, but we specifically went to the Norfork gauge for this project. And then on the Army Corps of Engineers side, they have the lake levels. So how high is the lake in both Bull Shoals and Norfolk for the lake? And then also another key thing that affected the model was the weather. So such as precipitation, the heat, how cold it was, anything like that is going to either A, affect the lake level, or B, affect how much power people are using in general. And one of the big things to realize that we gained from the data understanding was that a lot of this model really has to do with how much power is the Army Corps of Engineers planning on actually powering for the day, because there's a very high correlation between how many megawatts they're planning on generating with how many watts actually get generated. The problem here is that they've switched the way that they did their predictions of what they thought they were going to do. So they would say, oh, here's our schedule for the week, 7 days, or here are the next 7 days of what we're planning on producing. If we had that data, it'd be way easier to actually have a better model. But since we don't, we had to kind of get the understanding and try to go into the minds of these Corps of Engineers. And then finally, we bring all that data together. We store it off in databases. And that's also one of the most important things, I believe, is that you want to store the data as raw as possible that you have. So we have this data also stored completely raw. So in case we need to make more changes to it, we can easily change it. So make sure that you're never deleting data or just removing it in general, because you'll never know when you might need to go make some changes to it to do more aggregations or something like that in the future. And then finally, another very important thing about understanding your data in general is to visualize it. I would say it's impossible to look at an Excel spreadsheet with 10,000 rows and 10 columns and trying to figure out what is even going on. It's hard for a computer. Well, maybe not hard for a computer, but especially for us humans, it's impossible to even see the trend at all if it's not visual and right in front of us. So you can see that down here, I have the original target variable from the raw data that we got in. And you can see that most of the days and the times that it's predicted, or the targets actually was under 20,000 cubic feet per second. But then we have some of these spike days, which are going to be either A, considered outliers, or B, they're going to be pretty decently hard to predict, since there aren't a lot of times where we had targets that high. But it's good to know what was going on with those points to just get a base understanding of what's happened. And I like to also make sure that I make sure that I visualize all of my data so that I can confirm that it's right. We actually had an issue where when we were going to our open weather API, we had a different API beforehand, which gave us way more predictions out in front. And we were like, oh, wow, we're going to be able to predict this out 7 days, no problem, because we're able to get all this data for free. Well, the data was free, but it wasn't good data. Turns out that the precipitation rates in inches that it had was actually not even accurate data. If you remember, we had that snowstorm back in February, and it said that there was no snow, no rain, no nothing whatsoever at either of our 2 points. But whenever we checked NOAA or weather.com, we were able to find out that there was precipitation was there, and they were not accurately reporting the data. So just because you're getting data from what seems to be a credible source, it's always important to make sure that you dig into the data even further, because it might look on face value that you're getting accurate results, but that's not always the case. And that's why we had to do the pivot. And that's why the cycle is nice also, is because you can go back and forth as you understand more about your data, as you understand more about your business problem, but your work is still moving forward. So let's go to the data cleaning. I would say that the data cleaning is probably 70 to 80% of all that data science is, because again, like I said, garbage in, garbage out. We need to make sure that we have data that can accurately be modeled, and it's actually representative of what's going on. So since this problem is based on time, so as time goes on, the target changes. It means that it's a time series model. So any missing values that you're going to have in your data is going to be extremely harmful to your modeling in general, because a key thing that you need to remember whenever doing time series is that you're using equal spaces apart in your data. So if you're getting points for every 15 minutes, then you definitely need to make sure that you have points 15 minutes evenly spaced apart. There were some times where the CFS value was actually missing. Maybe the gauge was down, or there were some problems with it in general. The data didn't get transmitted where we didn't have values. So what we did there is I did basically just a simple linear regression. So say there was 20,000 at time 1, we're missing time 2, and time 3 is 19,500. Well, then we're going to assume that since the rate was decreasing, that rate was roughly around 19,750. And that's something that you need to take into account always when handling missing values is one, what is the column that we're replacing actually doing? Does it make what makes sense? Does it make sense to fill out, say, a median of the column, the average maybe? Do we try to use trees to figure out what the data is? But that can be very computationally intensive. So I decided to opt for figuring it out with a simple linear regression model. Next, how do we handle outliers? So there's a lot of ways that you can handle outliers in data in general. The first one being, and the most common I would say, is to look at just a standard deviation of the data. So you normalize it, take the standard deviation, and then you go 3 standard deviations each way. So that basically means that 99% of the time this data won't be here. But remember, we're dealing with a time series problem where we need to keep these equally spaced intervals. So what that means is that we can't remove outliers from our data. We need to keep them there so that our model can learn from them and be more effective at training on it. There's also different regression models that you can use where you look at something called Cook's D. And I can go into that in more detail if people want to know after it, but I don't think it's really necessary right now. But that'll basically also tell you if there's a large influence from a certain point. So then the most important part of the entire data cleaning process that we did was actually transforming this data set into a supervised learning model data set. So with time series, the previous points are going to affect the points going forward. And the data set that we have was not set up in a way where we could easily look and see if it was a supervised learning model. So what we did is there's like PCF, ACF, which is just autocorrelation and partial autocorrelation factors. And what that does is it can give you an idea of what's the moving average of the data, how many points affect the points going forward. And then by using that, we were able to transform the data where we took these moving average components, we took the autocorrelation factors, and we were able to basically manipulate the data set to get it into that stage. And then finally, whenever you're doing the data cleaning, there's going to be business case changes. Like I said, I had gotten pretty far with Norfolk and getting that lake all set up and ready to go. But then we found out that we needed to also take into account Bull Shoals. Well, with that change, it's always good to keep in mind that more data can be added to your data sets. So try to make your code or your pipelines as generic as possible, where you can add more columns and add more data as you need. And you'll see the power of the data cleaning we actually did on this data in the next slide. So let's go into our modeling and the package that we chose. So one of the big things about this project is we wanted to use a new machine learning technology. There's sklearn, TensorFlow, Keras. I'm sure you've maybe heard of those if you've ever looked into data science at all, but those are kind of the common packages. But we decided to go to the H2O AutoML package. And well, H2O package specifically, but the AutoML modeling inside of it. And so the nice thing about this AutoML model is that it does a lot of the hyperparameter tuning for you. So we don't ever have to mess around with, okay, maybe this gamma value needs to be changed by like 0.01 or the learning rate's like 0.05. These are just parameters that are in there where the computer will figure them out for you what the optimal ones are based on your training data. And as you can see on the next point, we have before we process our data and we just put our clean data into the models. I just threw it into the H2O as well as just a simple multiple linear regression model. You can see that we had an R-squared value of 0.007, which is you can think of that as under 1% accuracy. And then even with hyperparameter tuning of the H2O AutoML model, we had a value of only 0.02, which is about a 2% accuracy. And what R squared is it means residual squared. So if you think of, if you have a line, say, well, it'd be more curved, but let's just say we have a simple linear regression line, and there's a point here, and the model predicted that we're right here. Well, the distance between the point and the line is going to be called the residual. And then you just square it and then add it up for all the other points, and then you divide by the number of points. So that'll give you the basically how well your model actually fits the data that you have. And then you can see that after we processed the data with data cleaning, we were able to increase it a whopping 82.7% roughly, or think of it like that for R squared. So by doing this, we were able to gain so much more knowledge by turning it into a time series problem. And one of the advantages of having it as a time series problem where it's supervised learning is that we don't have to train a model every time over and over again. And that was one of the biggest goals, was to have a simple pipeline where we can just load in our model and just insert our new points and then and get our prediction out of it. Whereas if we had done a more standard time series model, we would have had to retrain every day, which is one, computationally expensive, but two, it's just not as efficient. And it's not, I don't think it's the smartest way to handle problems like this, because if we're able as a company to make models that don't need a lot of tuning or don't need to be retrained all the time, we're going to get much better results. And the final model that we had was this stacked ensemble model. So right down here, I've kind of shown you what the stacked ensemble model is. So basically what it'll do it will plug it into a variety of the built-in models in H2O. So there's neural networks, random forest, and then generalized linear models are going to be the main three that they have for predicting continuous variables. So they all have their predictions, and then it goes into this thing called a meta learner. What that meta learner does is it takes the little pieces that each model has learned and outputs them to get an even better result. You can basically think of it as averaging a bunch of models together to get the best prediction. And one nice thing about that is if you think of a very simple decision tree, if yes, it's like, are the Chiefs going to win today? Is their score higher? Yes, they win. No, they don't. It's very binary. What's nice about the meta learner is it can be like, well, is Patrick Mahomes are they on offense? Is Patrick Mahomes about to throw a deep ball? Well, that might give you a higher percentage. So it adds probabilities in instead of base binaries, ones and zeros. It makes it more into a probability on the branches that it takes, basically. So now that we have all of our models built, we need to evaluate them, see what's happening, and what changes do we need to make. So H2O itself, with the AutoML model, gives us a lot of power to do the evaluation. It has some built-in functions that allow us to have a leaderboard of all the models that we trained. So whenever we do that AutoML call to make the models, what it does is you can choose how many models you make. I just made 20 models at a time, and then it'll look at all 20 models that it made, and it will spit out the best one. But something important to always remember whenever we're evaluating models is that we need to have training and validation data. So what training data is that's going to be the actual data that you use to build the model. So it's going to try to fit basically the best line between or in this case, the best plane in between all of the points that you have. And then it is going to return those results. Well, if you didn't use a validation data set, it means that it's going to train super close to those points. So since we're taking a random, since we're basically taking a subsample of the entire population of the CFS, we need to make sure that we're not only training on just we're not only training on just the points that we're looking at, because we need to be able to make predictions in the future. We don't know that what happened when it was 76 one day with 2 inches of rain and a lake level of this, that they're going to be pumping out as much water. So we need to have a bunch of other points to validate against. And the H2O package gives you a very easy way to put that validation data set into your model so that all models are scored against the validation set and they improve based off of learning from the validation set because they're never seen when they're training. And a typical split, if we were doing something that wasn't time series, would be like 70% training data. You could do 30% validation. Sometimes people like to do 20% validation, 10% test, where the test data is just completely unseen data by the model, and then you throw that in there. But for time series problems, you're definitely going to like to do 80%, 20% split, is what I've seen has worked the best for time series models I've worked on. And then again, you can make any number of models at one time on the model. And then here's also just or on the H2O AutoML. And here's just another representation of what that R squared value is. We have all these points. You would just square them so that the negatives don't cancel out. And then you add it all up, and then you divide by the number of points to get your R squared value. So now, how did we deploy this, and how did we allow people, or here, sorry, I forgot one more thing on this that I forgot to add. One thing that really gave us that was really good about the evaluation of the model is that if you remember, the Bull Shoals Lake is farther away than the Norfolk Lake. Well, we found out because of the way that the water drains into the lake, as well as how long it takes for the river to get to the gauge point, that you had to shift the data by about 2 days for the precipitation to actually affect the target variable, and 1 day for Norfolk. So that was just something that we were able to evaluate. Well, we had models when we shifted the data, we got that 0.847 R squared, but ones where we did not shift the precipitation, we were down to the higher 70s. So we were able to find out and get some more understanding of how does water actually affect this gauge. All right, now for the deployment. So everyone can try this if you have your phone on you. I'm sure most of you do. But using the Keyhole Convo app, if you text CFS to that 913-270-0360, you'll actually get the predictions that come out. So what you'll see on here is these are predictions on a day-by-day basis, and that's going to be what the average prediction is. Due to the data we had, we were not able to get hourly predicted data in the future, at least with the subscription that we had at the time. But we are showing what the current CFS is. So if you see that there's a difference between here, it's because right now in the 15-minute interval that the CFS is actually tracked, that's how fast it's going right now. But for the day on average, this is what we are predicting that the values will actually be. And then we also have this prediction interval. It's a 75% confidence interval. And I'm still trying to mess with that a little, because I think we might want to pull the confidence interval back even a little more, just to make it more true prediction-y. But as you can see, as the days go on, the interval gets wider, and that just has to do because there's more uncertainty, right? You have to remember that whenever we're making our predictions now, we're, one, taking forecasted weather data, and we know how right weathermen are. And then two, on top of that, we're also predicting farther out into the future where there's going to be more uncertainty. And I think that the last time I looked at this of how our results were doing after we've tweaked our day-to-day predictions, we are in that 80% range of getting our mean within our interval. So that's definitely great for right now. Great for right now, but the cycle always continues. One thing that's important in data science to remember is that it's a cycle. Data mining is a cycle. And just like we try to do here at Keyhole, we're always trying to improve our models, and we're always trying to make things better and more accurate. So one thing that we want to do is we want to work on improving our predictions to get it into an hour by hour basis. So right now, as I said, we were doing the day averages, but what we'd like to get the models up and doing is that we look at it at an hour by hour basis, hopefully by collecting more data from what the Corps of Engineers predicted that they are going to actually send out, because that's going to be a very important part, I still believe, of what the actual prediction is. So once we can collect that data, we can get a better API service where we're able to get hour by hour predictions out in the future. And then that will improve our model, improve our predictions, give better results to farmers in general. If they want to know what's it going to look like at 5 o'clock, they could then look at the predictions and see that. And then finally, we'd like to add more gauge points. So like I'd said, I had built this whole project in the idea that we can add more gauge points in the future. So adding more gauge points will not be a problem. All we need to know is the latitude and longitudes really of where they're at, where bodies of water are that affect them, and then we can easily take the code that I have now and allow it to do predictions on all of those points too. And yeah, so that's what we want to do. Oh, and we're also uploading it onto AWS. So we won't have it all running through the Heroku app, but we're trying to get it on the cloud too, because that's also a very important part, I believe personally, about data science, is having your data, one, easily accessible to everyone, but two, just using the cloud technologies, because they do give you a lot of benefits where you can just push APIs into basically like their databases, and it'll pull that data automatically for you. So I wouldn't have to write all these scripts where I'm like getting all the data and cleaning it. We can kind of use the automation powers of cloud platforms to do that. So this was also my first project that I really ever had to kind of be like the project manager on, I guess, or manage what was actually going on. So we used a Gantt chart to track development, where I basically predicted kind of how long I thought the tasks would take, and then put out, we'll do this task, we'll do this task. And I also followed the data mining process, where that's kind of how everything was built out. First, we did our data understanding, then we built out our data pipelines, then we did our data cleaning, then we did our modeling. Maybe we went back and did more data cleaning, came back, did more modeling, evaluate, modeling. It goes back and forth a lot, but at the end of the day, we were able to track all of that. We also did weekly stakeholder meetings to, one, get more business understanding, but two, just to figure out, where we were in the project, and just to hold the project in general accountable. And then finally, with the project, we were actually under budget and ahead of schedule. It took us a total of 158 dev hours compared to the 228 that I thought it would take us roughly to do it. So I'm very happy about that, because that means that now we're able to take models that we know almost nothing about with almost no data, and within a month we were able to get a working model that had this 85% accuracy. So especially when we'd be working with clients, we might even be able to do work even faster, depending on how their data set is and how much data we actually have to collect ourselves. Because like I said, again, getting the data, cleaning the data, that's going to be your toughest problem. But every data science project I've really ever consulted on, they usually don't have good data. It's usually pretty bad. So we'll have to see as on a case by case basis. But we at least know that using this technology, we can get models deployed quickly to our clients. All right. Are there any questions about anything?
Can you elaborate on resource requirement? I think our folks might be interested in the infrastructure and the requirements of it's going to have. And this may not be a huge one, but it's a big deal, right? Because you got to have some computing power or storage.
Right, definitely. So one thing that is kind of a con about the auto ML is that it does take a lot of computing requirements to do. I was training the models on my computer, and it would take to make the 20 models where they were tuned and everything, it would take about I would say probably anywhere from 45 minutes to an hour and 45 minutes, depending on what data source was going into the model. And it would also completely take my computer out of commission, basically. Like I couldn't even try to go on the internet because it would lag so bad. So one thing that I had talked to about Jamie and Justin was actually having our own H2O server set up on AWS. So in the future, we could port in to that server that's already running on the cloud, and then we can train models locally, but we'll be hitting the server that's on the cloud when we initialize the model. So that'll give us a huge boost in speeding up the time it takes to train models.
What's interesting about this is the models, once the model's done, he simply just, Convo just has a little JSON file that has those predictions. So all this
Right.
effort results in just a prediction for those 4 days that we post to Convo, and Convo's reporting that, and it updates every day. And training of the model happens once, right? And then, so the model is in place now, and it's going to apply predictions forward based upon how do you bring in the new, right now it's pouring down in the area. I know,
Right.
tons and tons of rain impact. I mean, so that's going to show up. How does that is it retrained, or is it just feed into the model without retraining it?
So the model's not actually being retrained every time. That was kind of one of the advantages of using H2O, but also doing the time series supervised learning model, where we did the data cleaning with the moving average and the auto regression in the models. So what that does is it means that we don't have to retrain the model, but in the future, it might be good just to go look back at it and retrain as we've collected more data, specifically for the model. And I would doubt that there would be much change, because we were actually looking at so many days and we had so much back in time that I don't think much would change. But it's definitely something to look forward to in the future, especially if we can get that power schedule data set added into it.
Gotcha. Thank you.
No problem. Are there any other questions or anything?
I have a question. This is James. Yeah, thanks for the presentation. For the bad data, what did you guys did you have to dispose of it, or did you guys kind of updated it to make it fit what you guys were predicting?
So there was kind of a lot of things that we had to do. So the first thing that I just to reiterate, is that with doing time series models, you don't want to throw away your observable data points, because it's very important for model training that you have equally spaced intervals throughout the entire thing. So what we did is we were actually able, since we took an aggregate and we were predicting on the average of the day, we were able to kind of average in the outliers, first of all, but two, I also really like using the interpolation feature in pandas, which basically means that if the lake level was 651 feet and then the next day it was 650, and there's that missing data point in between, we would say that it was 650.5. So we do have to, you have to kind of think about the problem, I would say, and what would be actually happening. Does it make sense that the lake would be decreasing over time, but then one day in between it's just going to spike up? I would say no. So that's kind of our how we handled the lake level data. But for the problem, it kind of depends, right? If you were looking at a data set that had customers in it, and we were looking at the ages of customers, and all of the customers were, say people from a nursing home, you wouldn't change the ages there to people who are 20 years old. You might take a median to fill in those missing values, but a lot of it is just a case by case basis. I usually generally like to use the median for continuous variables or maybe categories, but there are also ways to do kind of like decision trees, basically, where we train a model on everything but the column that we're trying to fill in missing values for, and then it would make that the target and kind of predict what the model thought that the values might be. But like I said, that one's pretty computationally expensive. And I personally wouldn't use it on like my machine or something, but if I was on like a much more powerful computer, I definitely would do something like that. Does that kind of answer what you were looking for? Or is there something you wanted me to go in more detail about?
Yeah, that's good. Thank you, Alex.
Yeah, no problem.
There's a Chris Vaught had made a comment about Azure and AWS having ML tools. I know we talked about that. I'll say
Right.
we went with AutoML. We knew it. We were aware of that, but it's open source, so it was free, and
Correct.
those can be pricey, as Chris points out. We could have done the
Yes.
same thing with those tools, no problem, right? Built a model. I'll let you chat on that a little bit.
Yeah, for sure. I know that I'm pretty sure Azure has a built-in kind of AutoML model too. I just know that from what I've used, I actually did some cloud computing stuff in college a little bit where we would have to train models. And I remember one time I accidentally left my server on for like 2 days and I ended up getting charged like $150. So I was like, well, I don't want to just be losing money that way. But in general, it is pretty expensive just to train the computer. The computing time's a lot higher, especially if you have any sort of GPUs or high RAM models. So I think the biggest thing for us, at least right now, was just the cost and to see, can we develop these models cheaply without having to use cloud computing, but still get the power that these platforms offer. And I think that it's a good happy medium. Whereas, yes, you can develop models pretty easily in the cloud in general, but it's going to come at a cost, and the cost is money to develop the models. And you're not necessarily going to be building them any faster unless you're on like a super good machine. And then also another thing with the cloud platforms is that if you did make models locally on your own machines, you can still deploy them to endpoints in the cloud, where if they needed to, say, send in a couple Excel documents or something like that, or a couple rows of data that they wanted predictions out of, they could easily just drag and drop those predictions in, and then they would get the predictions back for each of the rows too. And we can do other things like that to have them maybe just click on this document, here are your predictions. So there's a lot of things in the cloud that we can do for deployment and handling the data too. As I would also say, it's good to keep it in the cloud because you just don't want to lose it.
Great, thanks.
Is there anything else from anybody?
Really good, Alex. Thank you for doing that.
Yeah, no problem.
Yeah, thanks, Alex.